So in the previous examples, we've looked at cases where we had an improper integral where either the lower or the upper boundary, well, in both cases they were lower, had a discontinuity. But what if there's a discontinuity in the middle? Like looking at this third example from our packet, what if we want to integrate from 0 to 3 of 1 over x minus 1? And also, I wanted to mention, this is a very common problem that I've seen students mess up hundreds of times. Well, that might be an exaggeration, but many times. But it's something where you might not even catch the fact that it is improper. Because first of all, if we're ignoring the details of the fundamental theorem, we might just think, well, the antiderivative of 1 over x minus 1 is the natural log of x minus 1. And if I'm just looking at 3 and 0, those don't really seem to be problems with the antiderivative. Because if I plug those in, please don't write this in your notes. If you are, just sort of showing you how to do this problem incorrectly. Well, the absolute value of 3 minus 1 is 2. And the absolute value of 0 minus 1 is 1. So what I would end up with is natural log of 2 minus natural log of 1. And it would appear as though this answer is the natural log of 2. But this answer is very wrong. This is not correct whatsoever. Because, again, this is improper. There is a discontinuity in between. And if you look at the graph of such a function, x minus 1, it looks like a reciprocal function just shifted 1 to the right, kind of like this, with a vertical asymptote at positive 1. Like so. And the issue is if I'm integrating from 0 up until 3, there's a discontinuity in there. And again, if there's a discontinuity either at the left endpoint, at the right endpoint, or somewhere in the middle, you can't use the fundamental theorem of calculus. It's not proven for such cases, and your answer will be wrong. So basically, how you want to do it is split it into 2 and think about it as 2 separate improper integrals. So basically, if I use that asymptote, which is at 1, to split my integral into 2 parts, I could think about what is happening to the left side of that and calculate that area, just as we did in previous problems. And similarly, I could take the right-hand side and do that as a separate integral. Basically, break it into 2 parts and go from there. And that's exactly what the third sort of case is saying for a type 2 improper integral. That if we're integrating from a to c, where there's a discontinuity somewhere in between, say at b, we want to split this integral into 2 parts, from a to b and b to c, and calculate them separately. Because at b, there is a discontinuity in the form of a vertical asymptote. We want to see what happens as we approach the asymptote from the left and from the right. And again, kind of imagining here, I want to see, well, is this convergent or not? Is this convergent or not? And I want to consider them separately. So let's go ahead and do that. So basically, I would start by saying, what's the integral from 0 to 1 of 1 over x minus 1? And notice now it's more apparent that 1 is a problem in this function because it's undefined. And similarly, I want to integrate from 1 to 3. But basically, just using property of integrals, breaking it down into 2 parts. Because if the area from 0 to 3 is convergent, then so must be the parts individually. And again, I can tell that 1 is a problem point on this function. Let me use yellow for this one as I have in my drawing. Sorry, those yellow and greens are kind of hard to tell apart. Apologies if you're colorblind. But yeah, so basically now we're just going to approach it in the exact same way. So it's improper at 1, so I need to take the limit as t approaches 1 from the left. Again, when it's on top, it's going to be from the left of 1 over x minus 1 dx. And then I would need to solve that integral, figure out the limit, and then I can move on. And then the second part here is the limit as t approaches 1 from the right. Actually, let's not reuse t. It's probably poor algebraic choice. Let's just say j or whatever variable you want. T isn't, there's nothing important about using t of 1 over x minus 1 dx. Or you could use s or m or, whatever. But essentially, I want to know, what's happening as this integral gets closer and closer to 1 from the right, which is the green segment of area, and what's happening as I get closer and closer to 1 on the left-hand side to see if those converge or not. So we already know the antiderivative of those. So, again, the flavor of how we do an improper integral, mathematically speaking, is, well, extract the limit, solve the integral, plug it in, and solve the limit. So it's, if we know how to do the integral, well, that's the natural log of x minus 1. I am allowed to do this integral because it's continuous from 0 to t, assuming t is getting closer and closer to 1, right? It's continuous over here. It's just not continuous at 1, but this is the workaround. And again, with the secondary component, the limit as j approaches 1 from the right, the integral of this would be the natural log of x minus 1 from j to 3. And I need to plug in my boundaries of integration. Sorry, not giving myself quite enough room here. But the graph, my point is the graph is very helpful. Whenever you're solving a definite integral, you want to be careful, especially with rational functions when they include asymptotes. Because if you're integrating over an asymptote, you can be introducing such problems as the integral being improper, and perhaps it may not converge at all. Another point I wanted to show you is that the exact opposite case of convergent is true for vertical asymptotes, that if p is 1 or greater, it will diverge. If p is less than 1, it will converge. Like, notice how this one had a exponent less than 1, it converged. This one had an exponent greater than 1, it diverged. It's actually the exact opposite case as before. And if p is equal to 1, it actually neither will converge, mainly due to symmetry. But again, you can always just do the math to figure that out. But now we need to plug in our boundaries. Again, this, I forgot to close my absolute value because there's a 1 and 1 in absolute values. Don't really play very nicely. But we'd have the limit as t approaches 1 from the right. We'd have the natural log of t minus 1. And then plugging 0 in would give me ln of 1, which is 0. And on the other one, I'd have the limit as j approaches 1 from the right. And this would be of ln of 2 minus ln absolute value. So I'm running out of room here. Let me just write it below. J minus 1. So plugging in my boundaries here and here. And basically now I need to figure out limits. Well, the limit of ln2 is ln2. But the limit of these, what is that? And notice that what I have here is the natural log of t minus 1. So again, this is a limit that you might not have memorized or might not recognize. So with this one, if I'm imagining plugging in 1, obviously I can't because that would give me the natural log of 0. But basically, it's going to approach the natural log of 0. And another thing to remember is the natural log of 0 is undefined, but the limit as x approaches 0, one of the kind of, this is mathematical garbage. This is not true. Because if you remember the graph of a natural log, it has a vertical asymptote at x is equal to 0. As you get closer and closer to 0 from specifically the right-hand side, it will trend towards minus infinity. But basically, this is a limit that heads towards minus infinity. And that's just because I know that. But so what if you didn't know that? How would you figure it out? Well, going back to Calc 1, there's a lot of different ways you can solve limits. You can solve them numerically. You can solve them graphically. You could just graph this guy and see what it looks like. But if we were to do it numerically, let's just try. I would want to plug in numbers very, very close to 1, right? Because that's what a limit means. What happens is t gets close to 1. So let's just say plugging in 0.999, that's very close to 1 on the left-hand side. So I would have the natural log of, also I would need an absolute value. Technically, we probably could do it without it, but calculators have it, so why not? But yeah, let's just try using 0.999 minus 1. So the natural log as t minus 1 gets close to 1 from the left should be approximated by this. And notice what I get as well, negative 6.9. And this answers something that you might say, okay, what is this limit? How would I know what that is? But again, this is something where it comes in handy to know that as the logarithm gets closer and closer to 0, it is unlimited. It gets unlimitedly small. Like, notice that if I get even closer and closer to 1, it becomes more and more negative. So this is a little bit of a tricky limit, but what it turns out is this limit is minus infinity. Or summary, the area of this yellow region, this is this is what I was solving all the way through on this part. And what I've concluded is that is infinite, well, infinitely negative, because again, it's underneath the x-axis. This makes sense. And actually, the exact same conclusion can be drawn from this part over here. This would be positive infinity. the segment of green area. But another thing about infinity is those areas do not cancel out. Infinity minus infinity does not equal 0. And this is something we talk about in Calc 1, but this is something which is called an indeterminate form. It's just mathematical stuff that you should not be trying to calculate. And again, in such cases, we just say that the answer diverges because anytime you run into an infinity or minus infinity or a non-existent limit, technically those are all sort of the same thing where it's just another case of a limit being undefined. But anyways, the thing I wanted to point out with this example is even if you have infinity and a minus infinity, those will not negate each other and make 0. Even though notice the ln2 is the same answer that we got as we if we completely overlooked the problem of this being an improper integral. But again, anyways, this is a divergent answer. And just, as we finish it up, let's just see what the calculator does if we do it, if we type in this integral. I don't actually remember if the calculator recognizes that this is a problem or not. So let's just see what happens. If we try to solve it, it looks like it's struggling. It's thinking. Maybe it will get completely stuck on it. Interesting. No, it doesn't get stuck, but what we do run into is error divided by 0. And so if you ever run into such a problem trying to solve an integral, what that probably means is it's improper, and that probably means it's a divergent. Errors, again, are not necessarily synonymous to divergence because sometimes calculators run into errors for their own reasons. But nonetheless, it does actually realize that this is a problem, just as we can do mathematically by solving the proper limit.